Hi everyone, and welcome to the second lecture of Quantum Riemann-Roch by Alexander Givental. Please go ahead.
Thank you. This what you I hope see in my share screen is where we ended up last time. So specifically, I'm looking at this differential equation and this hypergeometric looking formula, which is a solution to give the base of solutions to this differential equation. And if you remember, we were talking about so this the differential equation came out from studying holomorphic curves or complex loops, holomorphic loops in the complex projective space and actually hypersurface of some degree L, which is here in the projective space. So kind of the main derivation is that we suddenly got hypergeometric equations from studying holomorphic curves, that is on that side of mirror symmetry where the invariance, Gromit invariance of space is supposed to be. While usually the differential equations come on the other side of the mirror, they describe periods of some holomorphic integrals, variations of complex structures. And so in some sense, we have crossed the mirror from one side to the other already because we found these differential equations in the theory of holomorphic curves. At the time when I discovered that it was winter 94, Maxim Kontsevich gave a talk at Berkeley in the colloquium Berkeley, where apparently he was talking about the same idea, that is studying invariance of space of holomorphic curves of hypersurfaces in terms of the ambient space. Ambient complex projective space. So therefore, in some sense, therefore, this problem of proving the mirror formulas conjectured by Candelas, Delavos, Green, and Parks was already reduced to kind of figuring out we're across the mirror, we're on the same side, and the only question is why this kind of simple compactifications of spaces of curves that I was using and the correct compactification that Maxim Kontsevich was using give not the same result, but different results are related to each other by some mirror transformations or some funny manipulations with formulas. We didn't manage to discuss anything that time because while he was giving a talk at Berkeley, I was giving a talk in North Carolina. But we exchanged a couple of emails, and what Maxim wrote to me is that he is trying to prove mirror conjectures by using Riemann-Roch formula. Frankly, I was totally perplexed. I had no idea what he was talking about, which formula, how to apply Riemann-Roch formula, what's Riemann-Roch formula, and what it has to do with anything here. Actually, we will figure out what he meant in the process of these lectures. But today, let's try to recall what Riemann-Roch formulas are in general. Let me start with not the quantum yet, but the classical ones. And let's start with purely topological account of that. So here is the formula itself, but we need to understand what the ingredients are. What we have here is two closed manifolds, X and Y, and the map F between them. The manifolds is not enough, they're just oriented. They need to be them complex or almost complex, or at least stably almost complex, which means that the tangent bundles are equipped with complex structure, or maybe equipped with complex structure after adding a trivial bundle to them. That what stably almost complex means. V is supposed as a complex vector bundle over X. And here is the formula. So there is this symbol F star, but these two F stars have two different meanings because this one is what's called in K theory. It takes a bundle on X and produces a bundle, a complex vector bundle on Y. It's a push forward operation, but in terms of vector bundles. And here the Chern character is characteristic classes of that bundle in Y, and this is Chern characteristic classes of bundle V and X. And this is a third class of relative tangent bundle. We still have to recall, what all those things are. But this F star, it's a push forward in cohomology theory, which we discussed last time. Maybe I can show you where we discussed it. It's here that there is so that there is a map from X to Y between oriented manifolds, and you embed X into some bundle over Y, and this induces the map in the opposite direction between Thom spaces of normal bundles, and therefore induces map in the right direction between the cohomology with some shift in dimensions, because what is used here is Thom isomorphisms. Thom isomorphism between cohomology of X and normal bundle, and Y normal bundle, X and normal bundle, and that involved Thom class. So that was, therefore, this push forward involves the Thom isomorphisms, two Thom isomorphisms there. And so now we are in, so that in principle, that construction can be applied in any abstract cohomology theory. And now we are in what's called complex K theory. So now if X is, so what's complex K theory? If X, actually it's not written here, but X needs to be a finite cell complex. So when there is that means that CW complex with finitely many cells, then K upper node of X, it is the following thing. It's equivalence classes of complex vector bundles over, well, X plus, it's X plus 1 point added on the side. Topologies like spaces with base points, and so X doesn't have base point. You add that base point on the side separately. But so complex vector bundles on X plus, equivalence classes with respect to stable equivalence. Stable equivalence meant that the bundles become equivalent after adding, possibly adding trivial bundles to each of them of appropriate dimensions. So it's not immediately obvious that this is a homotopy invariant of the space, but it is because it has this interpretation. It's actually the same as homotopy classes of maps. This pi means homotopy classes of maps from X to this space. So this Z times BU means that there's countably many copies of the same space BU, disjoint union. BU, it is a limit of, we talked with you about classifying spaces, the infinite-dimensional Grassmannians, classifying spaces for bundles with structure group UN, and when you, make UN sitting in UN plus 1 and UN plus 2, etc., so that you take the direct limit of corresponding spaces, and you get this limit space BU. And so it's kind of, you understand that a bundle of a certain dimension can be induced next by map to BU from the universal bundle, and but if you want to stabilize it, you need to pass to the limit when n goes to infinity. So that's why the space BU appears there. But then there is a celebrated Bott periodicity theorem, which says that actually that this space is homotopy equivalent to the loop space of the group U itself. That's base loop spaces of U, and which means that the way how you construct the graded cohomology theory, that's K node. You take K1 to be the homotopy class of maps from X to U to the direct limit of unitary groups. But then, which is actually the same as the loop space of BU, or it's the same as homotopy class of map of suspension of X to BU. But then the next K2 is supposed to be something else, but it's actually because of this periodicity, so it becomes the same as K node. Therefore, this K theory is actually it's K node, K1, K node, K1. It's too periodic. But in any way, so that when V is a complex vector bundle over X, then it represents an element in that K node of X, which actually is a group with respect to direct sum of bundles, and it is a ring with respect to tensor multiplication of the multiplication induced by a tensor product of vector bundles. Now, okay, so this is kind of full-fledged abstract cohomology theory, and there is also a notion of Thom isomorphism. There is Thom isomorphism in K theory, and so that's what it is. So there is some finite cell CW complex X, and there is K dot could be 0 or 1 of X. Then it's actually isomorphic to. So therefore, suppose that there is a complex vector bundle V over X. It's not ZV that was there, it was just some complex vector bundle. And there is a Thom space of it that this picture shows. It means that I take at one point at infinity to all the fibers, which are complex vector spaces. Then this K tilde of the Thom space, it is tilde means that it's relative K group modular this base point at infinity, and there is an isomorphism. It should come with a shift of dimensions, but the shift should be by the real dimension of Cn, but it is even, and this dot is grading is to periodic, therefore it actually is K naught is identified with K naught. Now the way it is defined is similar to what happens in cohomology theory. So if you take this time take a bundle, so element alpha in K theory of X, you can pull it back, that pi be the projection from the total space of a bundle V to X. So you can pull it back to the total space of the bundle, but it's doing nothing because the total space of vector bundle is contracted, is homotopy equivalent to the base of it. So just pull it back, but then you tensor it with the Thom class, which is a class in K theory of the Thom space relative modulo the boundary, modulo the point at infinity. And therefore, this tensor product is already a relative class, and that's why it belongs in this group. So that is, and that the claim is it's an isomorphism. And so the question is, what is the Thom class in K theory? And this green formula is supposed to explain what it is. So namely, you have this vector bundle V, and again, you can take the pull pi star, but you can pull it back so that you can consider that we have a point in the Thom space. It is point V, it's one of the fibers Cn of that vector bundle. And there is a space, the vector space of that vector bundle corresponding to that fiber itself. Now, if you take that vector space, you can consider its the exterior powers of the dual vector space. So consider this exterior algebra of it. And but because we are sitting at some point, there the point is a vector in that vector space, and you have this operation of contraction by that vector, and you have this complex. It's a sort of causal complex. You take an exterior form, substitute the vector V, substitute twice, it's a zero already. Now the point is that when you're sitting on the zero section in X, when V is zero, then of course this contraction is a zero operator, and the cohomology of this complex is just the complex itself. Therefore, it's the corresponding to this complex element in K node of the space. It's lambda node minus lambda 1 plus lambda 2 minus lambda 3. It's alternated sum of exterior powers of the dual bundle. It's what is written here. But when the vector V is off the zero section, so it's no zero vector, then this complex is acyclic actually. So there is no cohomology in this complex, which means, in other words, that this alternated sum of exterior powers outside of the zero section is zero as a virtual vector bundle. So the sum of even exterior powers is isomorphic to the sum of all exterior powers, and the isomorphism is kind of established using this contraction by non-zero vector V. So in other words, this alternated this expression, so this virtual vector bundle on that space is a relative modulo of the complement to the zero section, a particular relative modulo that point at infinity. So it vanishes outside, well, everywhere there. And that's why it belongs to this K group of the top space. And that's why when you tensor with it, you get a relative element of relative K theory. And so this map is well defined. By the way, it's the same as in homology theory. If you restrict that Tom class, which lives here, to the zero section, that is, you take what I said before, just the difference, forget this, not equal to zero, forget, just take this difference, even exterior powers of V star minus odd ones, that's the K theoretic Euler class. So when you remember the homology theory, if you have Tom class and you restrict it back to the main space itself, then you get the Euler class of the bundle. So this is a K theoretic version of it. Any questions? Any urgent questions? Anything else? Okay, no questions. Okay, so therefore, the point is that in this formula, this F star means taking push forward using the Tom isomorphisms in K theory. That is, Tom isomorphisms involving this Tom class and this operation, this construction. Now, and this F star is a similar operation that we discussed last time in cohomology theory, using cohomological Tom classes. Now, what else? Chern character there. The Chern character is this characteristic. So it's actually, yeah, it is. So it is a characteristic class of a vector bundle, but it defines a ring homomorphism. In fact, it is, so if you take direct sum of bundles, then its Chern character will be the sum of the corresponding the Chern character of the summons. And if you take the tensor product, then Chern character is a product of the Chern characters in the cohomology. So, and in fact, if you tensor with K groups with rationals, and it is an isomorphism. Over Q, it is isomorphism. So the way it is defined is the following way. So if the vector bundle is a sum of line bundles, then, and let's x1, xn denote the first Chern classes of these line bundles, then the Chern character of the sum, it's e to x1 plus etc. e to xn. So imagine if you have another, add to this another group of line bundles, you add another such expression with different x's, so that's why it's additive. But if you multiply tensor such sum with another such a sum, then you can see easily that it actually is the sum, it's a similar expression with first Chern classes of pairwise tensor product of the line bundles, so that it's additive and multiplicative. But and it's defined over rationals because exponentiation requires some denominators, some factorials. But in any case, it is a symmetric expression in x1, xn, and therefore, if you write it in terms of elementary symmetric functions and replace the symmetric functions with excuse me, with Chern classes of the bundle, then it makes sense not only for direct sum of line bundles, but for any vector bundle. So that's how it works. It's a splitting principle that discussed last time with you, that if you, that the cohomology of the classifying space BUN is subring symmetric functions in the cohomology of the classifying space of n-dimensional torus, and for that reason, you can describe characteristic classes of complex vector bundles in terms of symmetric functions, and that's how it works. Therefore, this is definition of the Chern character. So therefore, this in this formula, therefore, that you take push forward in K theory of V, and you want to know its Chern character. But the claim is that, well, the question is how to compute it in terms of cohomological push forward in cohomology from X to Y. And this is sort of a general abstract problem. Namely, imagine that you have, well, just what we have here is two abstract cohomology theories. In this case, cohomology and K theory, and there is a morphism, multiplicative and additive, multiplicative morphism between the cohomology theories, the Chern character. And then if X and Y are manifolds with appropriate properties, so that the Thoma isomorphisms are defined for maps between X and Y. Thoma isomorphism defined for bundles over X and Y. In K theory, in this theory, and in that theory, which is the case when these manifolds are stably almost complex. Then there is always such a square. So if there is a map F from X to Y, you can take push forward in one theory and can take the push forward in another theory, but also there are these morphisms. And the question is whether this square is commutative. The answer is no, it's never commutative. That is, if you take push forward in K theory and then compute Chern character is not the same as computing Chern character of that bundle V and then taking its push forward. But you need to correct it. And so the correction is this factor Todd class. So that it measures non-commutativity of that square. And the Todd class, what's here? It is the relative tangent bundle. It means that the tangent bundle of X minus pullback from Y of the tangent bundle of Y to F by F. So once again, it's a tangent bundle of X minus pullback from Y of tangent bundle of Y pullback by F. If there's vibrations, then it means that it is tangent bundle to the fibers. So it's a relative tangent bundle. And Todd is it is some characteristic class of that bundle. And in just abstract situation, it's always like that. So the Todd class of a bundle, it's a ratio of two Euler classes. The Euler class in this bottom theory and the Euler class in the top theory, and morphism applied to it. So therefore, that's kind of the universal abstract property. Whenever you have a morphism between two theories in such a non-commutative square, that's what the correction term is. So it comes from the fact that when you do Thoma isomorphism, then it's so that it's not the same thing. So the Todd class, the cohomological Todd class of normal bundle, it's not the same as Chern character of this exterior with this exterior algebra of this K-theoretic tone class. They differ, and so you always get such a correction. And so in our situation, see what it is. So it's so if bundle is direct sum of line bundles with Chern classes x1, xn, then what's K-theoretic? So that so for line bundle, it's cohomological Euler class, it's a first Chern class, it's x1. So it's K-theoretic class. K-theoretic is an exterior algebra of the dual of line bundle, means that it is L to 0 minus L dual. So that is Chern character is 1 minus E2 minus X 1. So this is Chern character of the difference of the trivial bundle and the dual bundle to L1. And so this ratio, it is the Todd class of line bundle, but then for direct sum of them, this expression. And then if you, again, as usual, if you express it in terms of symmetric function, express it in terms of elementary symmetric functions and substitute for the symmetric functions the Chern classes, then you'll get the Todd class of a general complex, of any complex vector bundle. So I hope that this formula, this x divided by 1 minus E2 minus x, it's a familiar expression. If it's series expansion gives you, well, it involves Bernoulli numbers, we'll encounter it very soon. But so that's the meaning, the purely topological meaning of this formula. Whenever you have therefore a map between stable almost complex closed manifolds, then the Chern character of push forward of its complex vector bundle, it can be computed this homological push forward of the Chern character of that bundle times the third class of relative tangent bundle. Cool. Any questions? Okay, so this is purely a topological description of this formula, but there is more context and content to it. Namely, the Riemann-Roch formula that we will be using in our context is the context will be rather algebraic geometry. So suppose that X is some, say, complex algebraic projective manifold. So you see that I'm writing K node of X and underlining just to emphasize that it's not the topological theory that we were talking before, but it's a different thing. Namely, K upper node of X in algebraic geometry, it is called the Grothendieck group of locally free sheaves. So Grothendieck group of complex of holomorphic vector bundles on X. And the Grothendieck group means that, well, you can consider vector bundles, you can take the direct sum, you consider equivalence classes, take direct sum of them, but it is a semi-group. And the Grothendieck group, you make a group of it the same way as you from the group of natural numbers make a group of integers. You consider formal differences. So that this is an example of such formal difference, right? So that whenever you have, say, such a complex, you can consider alternated sum of these elements as an element of the bundles as an element of the Grothendieck group. This is kind of cohomology theory, because if you have a map from X to Y, then actually the natural map, if it's bundle over Y, you can pull it back by a map to X. So that the K upper node is mapped in the opposite direction. It's cohomology theory. On the other hand, there is this kind of homology theory. It's a K lower node of X, which is the Grothendieck group of coherent sheaves on X. And there is this map from, we have a holomorphic vector bundle, you can consider the sheaf of its sections, which is a locally free sheaf. So there is a map in this direction. But when X is non-singular, then it's known to be an isomorphism, and it kind of plays the role of Poincaré isomorphism. So it is from cohomology theory to homology theory. Namely, the kind of the inverse map is constructed this way. If S is some coherent sheaf, then actually you can have a finite locally free resolution of it on a singular manifold. That is resolution by sheaves of sections of holomorphic bundles. And therefore, the class of S in the Grothendieck group is the same as alternated sum of F naught minus F1 plus F2 minus F3, etc., which means that it's something that comes from under this map from K upper node. Yeah, but the reason why coherent sheaves, the Grothendieck group of coherent sheaves plays a role of kind of homology theories, because when there is a map from X to Y, then there is the natural map is forward. So there is a map from K lower node of X to K lower node of Y, and that's how it is constructed. So it should be, so yeah, so you have some sheaf on X, or maybe the sheaf of sections of some vector bundle on X, and what is push forward of it to Y, that F lower star of it. It is a sheaf on Y. You need to describe what are sections of it over some open set in Y, open set U. And what you do, you take inverse image of that U in X, and that inverse image of it, and compute, well, say, check homology of that inverse image with coefficients in the sheaf of sections of that bundle V, or coefficients in that sheaf. That is, H naught would be just the sections of that bundle, but there are high cohomology or high direct images, and so you take this alternated sum, and that's what considering as an element in the gradient group of sheaves, and that's what this push forward is. And by this isomorphism, it actually corresponds to some element in K upper node of Y. Here is an and so the point is that there is within this algebraic context there is exactly the same Riemann-Roch formula as we discussed before in topology, and it's called Grothendieck Riemann-Roch formula. It's from 1957 work by Grothendieck. So the formula looks exactly the same. So if you want to compute the Chern character of this push forward, then it is defined by cohomological push forward in terms of involving the Todd class of the relative tangent bundle. Here is a classical example which explains in the name of this formula. So when X is surface, Riemannian surface of the complex curve, some genus G, and Y is a point. So push forward to a point, it means just computing alternated sum of dimensions of Czech cohomology. H node, therefore L is a line bundle, a holomorphic line bundle over the curve. H node, it's a space of global dimension of the space of global sections of it. And there is this first Czech cohomology, which actually, according to Serre duality, is so that H1 of sigma with coefficients in some holomorphic line bundle L is dual to the space of global sections of a different bundle. Here it's a dualizing sheaf, or just it's on a smooth curve, it's a cotangent bundle. So therefore we're talking here about global differential forms on sigma with values in the dual bundle, line bundle 2L. And so the dimension of that space, it's what is here. So there was this difference of dimensions. It is it's called holomorphic characteristic of that line bundle, according to the Riemann-Roch formula, is given by such an integral. But this is a two-dimensional manifold, and so we need to extract from this expression the terms of degree 2, and exponential gives you the term C1 times 1 from here. And this expression, this ratio, that's the Todd series, right? So it's x divided by 1 minus e2 minus x, it's 1 plus x over 2 plus, so it's almost an even function. The only odd term is this x over 2, and the rest is an even series, and coefficients are called Bernoulli numbers up to these factorials. But in this dimension, only that x over 2 plays a role. Therefore, it is the first Chern class of the tangent bundle to the curve. 1/2 of it so need to be integrated over the curve. So this gives us a degree of the line bundle. It's therefore, if you have a meromorphic section, it's a number of zeros minus number of poles. And here is, so it's a first Chern class of the cotangent bundle integrated over the curve is the Euler characteristic of the curve. So it's 2 minus 2g, and 1/2 of it is 1 minus g. And this red color means that there was some typo in what I wrote first, and I corrected it later, so that it's using red pen. So that's the classical Riemann-Roch formula for curves. There is another interpretation of rather this the holomorphic characteristic, or of instead of Czech cohomology, you can use Dalbo cohomology. It's more analytic approach. Namely, so that holomorphic characteristic of M with coefficients in some vector bundle V, which is the alternated sum of dimensions of Check cohomology is the same as alternative sum of dimensions of Dalbo cohomology, which is homology of this complex. So you have differential forms on M with values in the vector bundle with, it's a smooth differential forms with zero, with no holomorphic differentials and any number of anti-holomorphic differentials. And there is this d-bar operator that increases the number of anti-holomorphic differentials by 1, and the cohomology of this complex is they have the same dimension as this. It can be identified with check cohomology that I mentioned before. But so far it still uses complex structure, holomorphic structure, the manifold and the bundle, but in fact there is a more flexible approach which doesn't require holomorphic structure. Almost complex structure would be sufficient, and namely the same number can be interpreted as the index of some elliptic operator. The operator is it acts from, you see that it's differential forms of with even number of anti-holomorphic differentials to formed with odd number of anti-holomorphic differentials, and the operator is d plus the adjoint operator d bar with respect to some Hermitian metric on Hermitian inner product. And it's called Dirac-Dalbo operator. And so kind of the toy version of what's going on here is a finite dimensional one, if you wish. So imagine that you have some complex, say, finite dimensional spaces. Well, C0, C1, etc., and some boundary operator, co-boundary operator D. Then there is a dual complex. There is this C lower, not C lower, and there are dual spaces, and there is a joint operator transpose. The operator going in the opposite direction. So there is this other complex. And then imagine that you introduce Euclidean or Hermitian, positive definite Hermitian structure in the spaces C, naught, etc. Then it identifies the spaces with the dual ones, and so you and identify the corresponding kind of homology and cohomology. But what you can say here is that the cohomology of, so you can think that D and D bar act in the same spaces. D increases degree and D star decreases the degree. Then the Euler characteristic. First of all, there is this elementary exercise in linear algebra that the that cohomology classes of the complex are uniquely represented by harmonic representatives, those which lie in the kernel of D and the kernel of D star. That is, the kernel of D star inside the kernel of D is orthogonal complement to the image of D, and so therefore it gives you the same, gives you cohomology. But then alternated sum of cohomologies, that is Euler characteristic of the complex, is the same as so that's super dimensions, alternated sum of dimensions of the cohomology, but it's the same as the kernel of this Laplace operator. So that it annihilates exactly those elements for which D is equal to 0 and D star is equal to 0. But also you can interpret it as an index of D plus D star, which acts from the sum of even graded spaces to the sum of odd graded spaces. And that's what is here is kind of infinite dimensional version of this. And this is called the corresponding Dirac operator. In some sense, it's a square root of the Laplacian, because if you take it square, then you'll get, well, D square is 0, D star square is 0, and what is left is D star plus D star D. And Dirac, probably physicists, if there are any physicists here, they probably know it better than me. So Dirac actually was trying to come up with a theory of electron, quantum theory, relativistic theory of electron, which is particle of spin 1/2, and he tried to have in mind this the case of spin 1, so that in electrodynamics there are Maxwell's equations, which are a system of first order differential equations, but they imply the wave equation, which is a second order differential equation. And so he tried to come up also with similar first order equations, but for since he needed the square root of Laplacian, and he invented how to take square root of Laplacian using quaternions. But then and this way he invented the Dirac operator. But he was saying that the equations that he invented is smarter than the author of that equation. And indeed he was right, because he discovered a very important general mathematical notion, some elliptic operator, which can be defined in very kind of non-rigid situation, not necessarily in holomorphic situation, but you can generalize it to spins, in this context, in spin C structure on the manifold, and using the index of that operator, that is dimension of kernel minus dimension of co-kernel, you can also define its holomorphic characteristics and push forward and such things here. Yeah, so a bit of again, there are some references here for some steps of the theory, namely this Riemann-Roch formula that I'm talking about can be interpreted also as a special case of Atiyah-Zinger index theorem for such Dirac operators. Namely, in 1959, Gelfand wrote this survey paper on hyperbolic differential equations, but somewhere he mentions there that if you consider elliptic operators, then the index is homotopy invariant. So it's that is the ellipticity is defined in terms of the principal symbol of the operator. And if you deform the operator such that principal symbol remains elliptic, then the index doesn't change. The operator remains Fredholm, so the dimension, well, the difference between dimension of kernel and co-kernel stays the same. And therefore, there has to be some homotopy theoretic description of that index in terms of geometric or topological data. And that's what Atiyah and Zinger did. They proved the index theorem, which computes the index in terms of the symbol of the topological properties of the symbol and characteristic classes. And that's what, so that this Dirac operator is one of such elliptic operators, but in fact, it doesn't, you can deform it away from being holomorphic if only the principal symbol remains the same, which is a purely geometric and topological object. Then the index will not change, and so therefore the index can be defined in more general situations than actual complex manifolds. But then, even before that, there was Hirzebruch Riemann-Roch formula describing the holomorphic characteristic of a complex vector bundle over holomorphic vector bundle over manifold as such a by such a formula, and Grothendieck generalized it to from mappings from X to a point. That was Hirzebruch did to from mappings from X to another space Y. And what I'm saying is that now that even further generalization can be obtained using a Atiyah-Zinger formula, and we can understand this. Therefore, what we discussed in pure topological context has also this analytical meaning in terms of Dirac operator, algebraic geometric meaning, and the formula looks the same, but it computes much more meaningful quantities, such as the indices of elliptic operators or holomorphic characteristics. Any questions to this kind of brief overview of Riemann-Roch formulas? Okay. Is it the right time to have a break, or? Okay. So now I'm going to talk about applications of Grothendieck and Riemann-Roch formula. The two applications actually. First is the one given by Mumford in his famous paper of 1983 toward the enumerative geometry of the modular spaces of curves. And the other is generalization of result by Faber and Carol Faber and Rahul Pandaripanda to the context of Gromov-Witten theory. But let's we start now with kind of going closer to the actual subject of Gromov-Witten invariance, and so the right now, therefore, we need to discuss dilemma for spaces. So that the spaces M, G, comma N without bar, and these are modular spaces of complex structures on Riemannian surface of genus G, the sphere with G candles, and with N distinct and numbered mark points. So the equivalence classes means that, well, the curves are considered equivalent if there is a holomorphic identification of them with sending mark points to the mark points. Now, the bar means that it's compactified by nodal curves. It means that the curve, well, an example of such a curve that so if you take hyperbola xy equal to epsilon, let epsilon go to 0, you get a union of two lines, and that's a model picture for a nodal curve near the node, right? And that's how a non-singular curve can degenerate into such a nodal curve. And the mark point is supposed to be non-singular, and the compactification is so the curves. The equivalence classes of such possibly nodal curves which participate in space are stable. So stability condition is the following, that the curve should have no non-trivial infinitesimal automorphisms, which in practice just mean the following, that in genus 0, if you have a sphere CP1 with fewer than 3 mark points, then it has a non-trivial group of positive dimensional group of automorphisms, so it's not good. So therefore, the number of mark points should be at least 3. When the curve is genus 1, then it should be at least 1 mark point. Otherwise, there is still some, there are some non-trivial families of automorphisms. But for genus 2 and higher, just no constraints at all. So anything at all. Now there is, so this picture, so we take this MGN bar and consider the space with an extra mark point, then there is projection here. It's forgetting the last mark point, but it also plays a role of sort of universal family of curves over MGN, namely, if imagine that there is some curve, for instance, this picture, this kind of line with self-intersection, just for example, it is, and it carries some mark point. This is a mark point with index I. So suppose that its equivalence class is a point in this base, or an MGN bar. The question is, what is the fiber of this map? And the fiber, okay, you need to bring in one more point. So you just take one more point on that curve, the 10 plus first mark point. So it looks like, therefore, that the fiber should be just the curve itself, except that the mark point is not supposed to be the nodal point and not supposed to be other mark point, because mark point is supposed to be distinct and non-singular. However, when you consider compactification, there was this n plus first mark point tends to the ice mark point, then actually what you're supposed to do, so okay, therefore the points over, so that space with n plus 1 mark point is just the same curve with the same mark points and this one more mark point on it. But when that point approaches in the fiber, approaches that mark point, then actually you're supposed to add a new component, rational component, CP1, and place these two mark points there. It will be, there are 3 mark points on this component, the curve is stable. So therefore this new curve represents, its equivalence class represents a point in that mgn plus 1 bar space corresponding to this point where the current point hits that ice point at that point in the fiber. Likewise, if that n plus first mark point tends to this node, then it's not allowed to be in the node, but you need to consider another curve. You need to disconnect these branches, but connect them by an extra copy of CP1 and place n plus first mark point there. And so therefore this is, so the result is the following, that the points in the fiber are exactly correspond to the points of the curve itself, including the node and the mark points, except that when it is one of those, then the corresponding curve that represents the points in that modular space is this modified curve. Therefore, the kind of the fibers of this projection are the curves themselves, which whose equivalence class corresponds to the point in the base. It's not 100% true because actually the spaces are orbifolds because curves can have some discrete symmetries. And strictly speaking, the fiber is a quotient of that curve by that discrete symmetry, if such discrete symmetry are present. But modulo that correction, it is just the fibers are the curves themselves, so that it's, you can think of it as. So here are a few examples. So if you take M03, then what is it? It's a sphere with 3 mark points. It's a unique object. You can make these mark points by choosing coordinate system, can make them 0, 1, and infinity. It's already compact, so this bar adds nothing. So M03 bar, it's 1 point. M04 without bar. Well, it's equivalence classes of 4 mark points on the sphere. And there is a cross ratio. You can make the first 3 points to be 0, 1, and infinity, but then the first mark point, it will be some complex number lambda, which is different from 0, 1, and infinity. So therefore, this M04 is CP1 minus 3 points, 0, 1, and infinity. However, when you compactify it, then this 0, 1, and infinity are added back because when lambda tends to 0 or to 1 or to infinity, then actually there are such curves which are nodal curves. There are 2 lines intersected at 1 point, and there are 3 ways of partitioning 4 markings into groups of 2. So when lambda tends to 0, it means that the first mark point and the first mark point are in the same component, and when lambda tends to 1, it means that the first mark point and the second mark point are in the same component, and when it's infinity, then means that fourth and the third mark point are in the same component. And so there are these 3 stable curves which represent the stable curves corresponding to forbidden cross ratio 0, 1, and infinity. At the same time, if you look at this whole picture, it is a surface fibered over this CP1 with fibers as is shown, and it is itself with M05 bar, as my previous explanation suggests. Yeah, so actually, this space itself can be described also as CP1, CP2, the projective plane, blown up at 4 distinct points. Namely, if you consider sections defined by mark points, as if, for instance, the first mark point here, 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 there, and the second is here, 2. So there are 4 sections defined by mark points. The sections are CP1s, and they have self-intersection index -1, as it turns out, so you can blow them down. If you blow them down, you get just CP2. But this whole thing is blow up of CP2 at 4 distinct points. But anyway, so that's what it looks like. In genus 1, another example, M11 without bar, it is just complex structures on the torus that is upper half plane modular SL2Z. So it is the usual modular picture that tells you that how to parameterize all elliptic curves. And it's known that this quotient analytically it is a complex line. It is isomorphic to C. But when you add bar, it becomes CP1, and so that the compactifying at that point, it infinity correspond to such rational curves with solve intersection. So that you consider elliptic curves as such cubical curves given by such an equation. Then when this so cubical equation, then it's the case when the polynomial requires double roots, so that its curve becomes rational with self-intersection. But also from this description, you can say that M04 bar is that M11 bar is the same as M04 bar modulo the permutation group of the three roots of this polynomial. It's also what it's CP1. And equations about this is just some kind of crash course on Dilley-Mumford spaces. Actually, there are some in the chat. There are two something. So, is there any questions there? Okay. No questions. So now let's talk about Mumford's paper. It's published in the volume dedicated to the 60th anniversary of Shafarevich, and it's quite an extensive paper which lays down the grounds for intersection theory on these Dilley-Mumford spaces. But one of the results, one of notable results there is the following theorem. So consider this. Well, let's take the number. What he does. He considers this mg bar with no mark points, and this universal curve over it. So there mg1 bar. And let's take on that space. We can take the trivial one-dimensional complex vector bundle C. And it's push forward, k-theoretic push forward downstairs. What is it? It is h naught minus h1. So h naught is just, it's if using a trivial bundle, it means it's just constant functions on the curve. So it is just C. It's the trivial bundle on mg naught bar. And h1 is, by sheer duality, it is the same as holomorphic differentials. The space of, it's a dual to the space of holomorphic differentials on the curve. Case dualizing sheaf, and it is called denoted by this blackboard ball E, and it's called the Hodge bundle. So its dimension is G, the genus, the number of independent holomorphic differentials on the curve. It's a vector bundle on, here. And so the question is, what are the characteristic classes of this Hodge bundle? They're called Hodge classes. And that's what Mumford theorem computes. He computes the Chern character of this Hodge bundle. And he computes it by Grothendieck-Riemann-Roch formula. So therefore, according to Grothendieck-Riemann-Roch formula, you need to take what cohomological push forward here of what the Chern character of C of one-dimensional trivial bundle is just one. It's trivial bundle, so it's one. And then you need to take the Todd class of relative tangent bundle, and so therefore that and push it forward cohomologically. So that's how his formula looks like. And first of all, it has different homogeneity components. So this Chern character has component 0, component 1, component in degree, could have component in degree in real units, degree 2, 4, 6, etc. In fact, it has something in degree 0, and the rest are in degree sort of divisible by 4. So it is no, not divisible by 4. Okay, so this psi is what's psi? Psi is the first Chern class of the bundle over that over this space, which at the point there is just the cotangent line to the curve at the mark point. So there is this is the modular space of curves with one mark point. At mark point there is a cotangent line, tangent or cotangent is tradition. We take cotangent line, and it's line bundle over that space, and it has its first Chern class. It's class psi. So it's a class of degree 2. So what is written here is psi to degree 2L, so it is degree 4L plus, but it take homological push forward, it becomes class of complex dimension 2L minus 1, therefore real dimension 4L minus 2. So in other words, with the exception of this constant term, all other terms are non-zero, not divisible by 4. They're not divisible by 4. So divisible by, well, mod 4, it's 2, 6, the degrees are 2 mod 4. So it's a part of the answer. Therefore, the somehow the components of Chern character of degree divisible by 4, except for this one, they vanish. Kind of makes sense if you think, because what does it mean that the classes, so that's the components of Chern character in degrees divisible by 4 vanish? It means that if you take the bundle and add the dual bundle, take direct sum with E star, then it's going to be trivial, or at least it has 0 homological. When you take duals and this terms of degree, which are 2 mod 4, they change the sign, and which are 0 mod 4, they don't change the sign. Therefore, when you add Chern character of E and E duals, then you'll get, except for this, you get 2G, you get 0. It kind of makes sense because you see that if E is holomorphic differentials or dual to it, then the dual is anti-holomorphic differentials. If you add them together, you'll get just the topological second cohomology get first cohomology of the curve with complex coefficients, which carries the lattice of integer cohomology classes, and therefore it has a flat connection in it. So at least if we are talking about curves which are not nodal but smooth curves, then the bundle E plus E dual carries a flat connection because it's purely topological object. There are integer lattices there which can be carried from one curve to the other. It doesn't depend on complex structure, and therefore in terms of local formulas for characteristic classes, there should be 0. But somehow this argument is not rigorous because there is a bar there, so there are not only smooth curves but curves with self-intersection. But nevertheless, the conclusion stays the same. So that this vanishing of some components suggests that this E plus E dual is topologically trivial, or at least flat. But anyway, so this formula, so how it is obtained? This G, it is 0 component, it is just a dimension of the bundle. In the Riemann-Roch formula, it comes from, see that where is this? So this is the Todd class. So instead of X, it looks like we should take psi there because it is the cotangent. So it is so actually minus X is cotangent. So psi is the first class of the cotangent line bundle to the curve at the current point, and we need to push forward, means integrate over the curves. There was this term X over 2 will give us the same as in the classical Riemann-Roch formula. It will give us this 1 minus G. That 1 stands for, it's for the dimension, 1 stands for the trivial bundle H node, and minus G stays for H1, for the Hodge bundle. But we changed the sign here, right? So we took not, so it used to be H naught minus H1, but we took just plus H1, this Hodge bundle. That's why it is G. So the G is just its dimension that comes from Riemann-Roch formula. The rest is, so then this term is exactly what you get by doing what I just said. You take x to be minus psi and push forward this term. So that's what's written here. It's taking this cohomological push forward from this space to that space, from this space to that space. It gives you these terms. But somehow there is some correction here, and that's kind of the main observation of Mumford. That's what makes this formula non-trivial and interesting. And here, so then I'll try to explain to this observation what it is about. Any questions so far? No. Okay, so okay, so what we're supposed to do, therefore, we are supposed to, according to the Riemann-Roch formula, we're supposed to take the relative tangent bundle to this map. Therefore, it is, yeah, for most of the times that for most of the fibers which are non-single, it is just the tangent bundle to the fiber, to the curve. And take the Todd class and push it forward. And that's what looks like that we're getting this expression from there. But we need to compare it to what exactly this psi is, because psi is the first-order class of the cotangent line at the mark point to the curve. And of course, it is the same, that's just the cotangent to the fiber, as long as that point is not the nodal curve, or nodal point. As long as the curve is non-singular, or even if it's non-singular, it's fine. But when the point becomes a nodal curve, then we should be careful, because at this point, we need to compare what is the relative tangent bundle and what is this bundle whose first-order class is psi. And here is how we can figure it out. This is essentially the dualizing shape, in fact. So, so the thing that local, let's consider local model of this situation when near a node. It means that there is C2 maps to C here, where C2 is just plane with coordinates x and y, and the map is product x times y. Then when x times y is equal to epsilon, then it is a non-singular curve, hyperbola. And when it becomes zero, it degenerates into a nodal curve, intersection of two branches, right? So in terms of this coordinate x, y, what are upstairs, what are sections of this bundle, the cotangent line and the mark point? So the claim is the section looks like that. So what is here? Phi is any function of x and y, holomorphic function, and this expression dx wedge dy divided by d x times y. So we cannot divide differential forms. There is no such an operation. But this expression correctly defines a differential one form on the fibers at non-singular points, at least. So, namely, it is kind of relative holomorphic volume on the fibers. It's volume on the in C2 divided by pullback of the volume on C. So it's well-defined differential form on the fibers. So this is kind of non-vanishing section of that cotangent bundle on the curve outside singularity, and then multiply by holomorphic function, you get the sections of it here. So what happens at the origin when x, y is equal to 0? So geometrically, what happens is the following. First of all, the curve needs to change. you need to add this component. And this cotangent line is not cotangent line to the curve here or there. It is cotangent line to this inserted component at that mark point. So it is kind of a trivial. You can think of a trivial line bundle because this CP1, this line, has three special points: this one, that one, and the mark point. So we can introduce coordinate system there and kind of trivialize, canonically choose coordinates, except that when you interchange these 2 points, then it causes a change of multiplication by -1 here. Therefore, it is sort of an Orbi bundle, which is kind of locally, it is, well, it's trivial on the double cover, if you wish. When you decide which branch of the curve is first, which is the second, then it becomes the trivial bundle. Otherwise, it kind of changes the sign. And that's exactly how this expression behaves if you take the origins of phi is just a constant, but when you interchange x and y, then this is because of this wedge, the sign changes. Maybe to understand better how what are sections of this sheaf, it's better to upgrade. These are one forms, but if you wedge it with differential of xy, you transform it into two forms, and it will be just some holomorphic function phi of xy times some standard volume form dx dy here. So that's how the sections look like. If you think in terms of holomorphic differentials, then really this bundle is the dualizing sheaf, which consists of sections are holomorphic differentials on the curve, but near the node, that holomorphic differential actually is allowed to have pole of the first order on each of these branches. But with the condition that the residues, when there is a pole of first order, that holomorphic differential, you can take the residue, and residue is just a number. It's trivial. It's a scalar. But the sum of residues on one branch and the other should be 0. And again, therefore, it's a scalar sort of trivial bundle. Just C. But when you interchange the branches, then the sign changes, right? Because the residue on one branch is opposite to the residue on the other. Therefore, if you decide that your complex number, this residue is related to this branch, and you interchange them, the sign will change. So therefore, this is actually the dualizing sheaf on the curve. But now let's consider what's a relative tangent bundle. And the relative tangent bundle, or cotangent bundle in this case, I'm talking about cotangent bundles. So what is it? It's by definition, it is a cotangent bundle to that in my local model to C2 minus the pullback of cotangent bundle to C. The possibly confusing thing now is that this bar here and this bar there mean different things. This bar, it's a ratio of these forms. This bar, it's a quotient. So this is a module of sections of, it's one forms, holomorphic one forms in C2, modular the, what? So that's the sections of the cotangent bundle on C pulled back to C2. What is it? It has section differential of xy, and then you can multiply it. It's one-dimensional bundle. You can multiply it by any holomorphic function. Therefore, it is this one forms modular forms proportional to the differential of xy. Again, to figure out what it is, what's this quotient? How to understand this quotient? You again can wedge with a differential of xy. Then the denominator will become 0 because it's something divisible by differential of xy. We wedge with differential of xy, you'll get 0. But when you do this with the numerator, that's what you get. The differential of xy, it's x dy plus y dx. And if you just multiply, you'll get ax plus by dx dy. So you see that, therefore, inside of this sheaf of all two forms and C2, you have the sheaf of two forms what is this? Is the ideal of functions vanishing at the origins, right? Ideal generated by x and y. Therefore, functions vanishing at the origin. Therefore, this relative cotangent bundle, it's not the same as this dualizing sheaf, and the difference is concentrated at the origin and the nodes. And it is just so essentially it's a structure sheaf of it's just a trivial one-dimensional bundle on the nodal on the nodal locus. And so that's what gives eventually this term in Mumford's formula. Therefore, we were doing the computation here. We were doing the computation with the Fecha class of this dualizing sheaf, but we had to instead do it with this relative cotangent bundle, which differs from it by you need to subtract the trivial bundle on the nodal locus. Therefore, in this family of cursors, this is MG node bar, and this is space fibered over it with fiber the curves themselves. There is this Z is a nodal locus, this pink thing. It's a codimension 2 stratum there. Its codimension, its image here is codimension 1, so these nodes appear with as a codimension 1 phenomenon. But upstairs, it's like origin in this line. But upstairs, it is origin in situ. It's codimension 2, and there is a sort of one-dimensional trivial bundle on it. And you need to take it, its Todd class, and push forward it by no, so actually not of it, but that's a correction to you need to take this bundle minus that trivial bundle on Z, and for the whole thing take the Todd class and compute. Okay, take this bundle, subtract that structure sheaf on Z, take the Todd class and push it forward. And the result is, so it's a couple of pages of computation with characteristic classes. Mumford's paper, when we needed to do the same with Tom Quotes in our paper, we managed to compress it to half a page, but still it's some computation, more or less routine. But so what's this answer? What's written here? So the correcting terms are concentrated on the image of that nodal locus upstairs, and so that is FT, the forgetting the mark point applied to Z. So it's codimension 1 stratum here, some compactifying stratum. It consists of what? So of it can be parametrized by the following thing. So it's a disjoint union of the following thing. So if you have a curve of genus G with no mark points but with self-intersection, it means that actually it has G minus 1 handles. This extra self-intersection counts for kind of another handle. And so you can disconnect these two branches, and then you will have a curve of genus G minus 1 with 2 mark points. And that allows you to parameterize such curves here. Or you can have two different curves of genus G prime and G2 prime with 1 mark point each, glued at the node. And this phenomenon is parameterized by this product of MG prime 1, MG2 prime 1 bars, where G prime and G2 prime is the sum give you the right genus. And so this disjoint union of many strata parameterizes the thing. And this mapping, parameterizing mapping is denoted as I. I is a mapping from this disjoint union to this stratum. I is it's a mapping, but it's an inclusion of, if you wish, an inclusion of this, so there's a map from this space to MG G node bar. And I star, it's a push forward of some cohomology class under this inclusion. And what's this cohomology class? Psi plus and psi minus are the cotangent lines, it's Fecha classes of cotangent line bundles at the node at these two branches. Therefore, here it is this one and that one, and here it is this or that one. So there are these 2 mark points, and here there are also this 1 and 1 mark points, and each one carries a corresponding cotangent line, and the Fecha classes are denoted psi plus and psi minus. 1/2 stands for the fact that actually there is a symmetry interchanging the branches or interchanging the these two branches when you disconnect. So these two mark points are numbered, but they shouldn't be. And so, therefore, you see that there is this class psi-12 living on that space, and you take it push forward, homological push forward here, and here there is a class living on this gadget, on this disjoint union, which is mapped to MG node, and it's pushed forward of that class by the inclusion there, by the parameterizing map. Okay, that's Mumford formula. So for the Hodge classes. Any questions about this? Okay. So now let's go to the Gromit theory. Namely, I'm going to, my goal now is to describe a generalization of that Mumford result by Carol Faber and Rahul Pandaripande of 1998, which is just kind of straightforward generalization. Again, they computed in some sense, the characteristic classes of the Hodge bundle, but in more general situation. So the Riemann-Roch spaces, from the point of view grown within theory, they are complex curve in the target space, which is the point. So there is no actually target space, it's just a point. But grown within invariants deal with holomorphic curves in more general target spaces. And so let's talk about this. So therefore, X now is say Keller manifold, or if you wish to do some symplectic topology, it's almost Keller manifold. And this MGN bar X comma D, it is the modular space of stable maps of complex curves sigma, comma, this sigma 1, sigma n, and the mark points, the curves with n markings, holomorphic maps to X, and some characteristics, discrete characteristic are fixed. The genus, arithmetical genus of the curve, the number of mark points is fixed, and the degree is fixed. Degree is the degree D is the following thing. So there is such a map, then the fundamental class of the curve represents some homology class, second homology class in the target space, and that's what the degree is. The degree is the homology class in H lower 2 of X. Now the genus G, it's well, if the curve is non-singular, then it's a number of handles, but in general, it's a dimension of H1 of that Hodge bundle, if you wish. It's the dimension of H1 of the curve with coefficients in the structure sheaf, in the sheaf of holomorphic functions, or the trivial bundle over it. Again, it turns out that the compactification of the spaces of such maps. Well, wait a second. Not the space of maps, but first of all, there is an equivalence. It's a modular space, so there is an equivalence. Equivalence is defined this way. So there are two such holomorphic maps. Equivalence is defined by identifying the domains. Therefore, there should be isomorphism between the curves, which sends mark points to mark points in the corresponding order. And mark points should be distinct and non-singular. Now, it turns out that such space can be compactified by allowing nodal curves, also just with simple intersections, nodal intersections. But they should be stable, and the stability condition is in words sounds the same as before. So if there is an equivalence of maps, then we should be able to talk about autoequivalence, automorphisms of map, and it requires that stable that the maps don't have non-trivial, infinitesimal automorphisms, or the automorphism group can be at most finite. In practice, it means the following: that see that because the automorphisms actually are defined only by transformation in the domain, which should give you, after application of the automorphism, the same map. Then if there are some components of your curve which are mapped non-constantly, like these green things, then they are stable dramatically. So that but the stability condition is the following: if there is some component CP1 which is mapped to constantly to a point in X, then it should have some three something, so three special points, either mark points or nodal points, or yeah, so that the parameterization can be fixed up to finitely many choices. And if there is a component which is an elliptic curve mapped to a point, then it must carry either a node or should carry or some mark point, but otherwise this stable, everything else is stable. So that's what means in practice. Again, there is some rather rich picture. If there is this modular space, then there is evaluation maps. I don't know why I wrote this arrow, so it should be this arrow. Evaluation at n mark points, mapping to x times x times x n times. There are, if you add an extra, throw in extra mark points, there will be this projection of forgetting that extra mark point, and the fibers will be more or less the curves themselves, which correspond to, which are domains of the maps corresponding to the point in the base. And again, if you can see the evaluation at n plus first mark point, it will be the stable map itself that corresponds to the point in the base. There are also, not shown here, but there are sections defined by mark points. So there are many kind of arrows that can be added to this picture. One of them is you can forget the map phi and remember the curve itself and hope that it is stable, so it represents some point in the Dirichlet spaces MG and bar. So it just has its complex, forgetting the map and remembering the complex structure. It doesn't have to be actually stable in the Dirichlet sense, but it means that you should contract some components of it, and then still this map will be well defined. Therefore, from each point here, you can forget the map and still produce a stable, the Riemann-Roch stable curve, which represents a point in the Riemann-Roch compactification of modular spaces of complex structures. At least when G, comma N is not in the forbidden range for the Riemann-Roch spaces. So anyway, so the point is that these spaces can be they can be actually very bad, ill-behaved when X is a Keller manifold. They can have kind of wrong dimension, be singular, have many components, but still it's possible to equip them what's called virtual fundamental cycle, which can be used to do intersection theory. So we can evaluate cohomology classes of that virtual fundamental cycle and define sort of intersection indices in this sense. And it's defined in such a way that kind of the intersections behave as if the space was of right dimension and was non-singular. So that it's some sophisticated foundational project solved by many people in different ways. So there are such virtual fundamental cycles. And so, therefore, Gromit invariants of X are intersection numbers in such spaces. When X is a point, then the spaces become the Mumford spaces, and that paper of Mumford of 1983 was developing, in some sense, Gromit theory of the point target space. Any questions about? No. So I'm going toward formulating what Faber and Penderipane did. And so here is some notations for defining how one defines Gromit invariants and how one makes generating functions of them. Well, maybe I should start with this line, which is correlator. So there are n seats. N is the number of mark points when I'm dealing with MG and bar X, comma D. So these AIs are cohomology classes of the target space of X. And the positions in this correlator, they correspond to the mark points, the first, second, etc., the ends. And so, therefore, what the correlator actually means, it is the integral, so evaluation on the virtual fundamental cycle of something, and that something is obtained this way. So you take these classes A1, AN, and pull them back by evaluation maps from the target space to the moduli space. And this psi is actually, it means that you take in the first position, you take psi1. It's a first chunk class of the cotangent line bundle to the curve at the first mark point, raise it to the power k1, and okay, it's cohomology class on that moduli space. And do the same with therefore this psi means that it is psi n. It's a first chunk class of a cotangent line at the nth mark point. And when you take this product and integrate, you get some number. It is because the this line bundles are actually orbi bundles. You get irrational number, not necessarily an integer, but anyway, this is how you define grown bit invariance. When you don't have psis, you call them just grown bit invariance, the primary invariance, and the meaning of them is that in what sense is intersection index, you require, consider the count curves which such that the mark points, the first, second, etc., are mapped by phi, by two cycles Poincare dual to the closest A1 AN. So therefore, you consider curves with constraints at mark points. And if this number is discrete and finite, you count it, and that's what this number is. But when the psis are there, they are called gravitational descendants. So the corresponding invariants are called gravitational descendants of those primary classes. Therefore, gravitational descendants means that the psi classes are involved. So that's what it is. And so then what you do, you form generating functions like that. For in genus G, you sum over, genus is fixed, you sum over all n number of mark points and all degrees. The degree, if you remember, it's a vector. It's a degree 2 homology class. It's a degree is an element of H2 of X at some letters. There, if you pick a basis in H2 of X, then therefore, it will be a bunch of numbers. So if a rank of that group is R, then you have an R tuple of integers, D1, DR. And this Q to D means that Q1 to D1, QR to DR. So it's monomial. These variables, that's called Novikov variables, and this cool ring is called Novikov rings. Actually, we already had this notation, and it is Gromov-Witten in this context, it's counterpart of those deck transformations that we had on the universal cover of the loop space in Floer theory, and they indeed correspond to elements of H lower 2 of X. So that so this is the group ring of that lattice. So the same Q's as we discussed that time. Now, what you this put in this correlator, you put T of psi, where T is T naught plus T1 Z plus T. It's T naught plus T1 psi plus T2 psi square, etc. So it is the kind of the general formal series in one variable with coefficients which are cohomology classes of the target space. You make this Novikov ring the ground ring, so therefore cohomology with coefficients at ground ring. But if you think what this this expression means and what understand that it's polylinear with respect to this inputs, then understand that it's just a generating function. It's a function in T's such that its Taylor coefficients are these particular correlators. So that is just a few, therefore just can encode them with such a series, which means that it's the Taylor coefficients of it at the origin will be these numbers. So therefore, on its own, it's a function on such space of series in one indeterminate with coefficients T0, T1, T2, which are vectors from the cohomology algebra. of the target space. And finally, what Faber and Rahul Panaripan do, they consider this, they combine all these generating functions into a single one, probably following what physicists in string theory are doing. So this is kind of partition function involving all genera. It intentionally looks like quantization of something, so that it is yeah, it is some kind of element of the Fock space. This Planck constant h bar to g minus 1. G minus 1 is minus 1/2 of the Euler characteristic of the curve of genus G. Okay, and so you have this generating function, which has an ugly name, the total descendant potential. So it involves, combines all together in all genera, all growing with invariance, the primary and gravitational descendants of the target space X. Now, what they do in their paper, they bring in to the intersection theory the characteristic classes of the Hodge bundle. Therefore, they do sort of the same thing that Mumford did, so that on this space they consider the trivial one-dimensional bundle, take its push forward, which is trivial one-dimensional bundle minus the bundle of dimension G, called the Hodge bundle, this E. And it has components of Chern character. As I already said before, that they turns out to be, in this case, turns out to be zero. It's rather outcome of this computation rather than of the theorem rather than assumption. It turns out to be zero for even k and possibly non-zero for odd k. So you consider such so therefore what is here? So the SK are arbitrary parameters, and you insert into this systematically in all these correlators, you insert this factor. It's exponential of the sum of k from 1 to infinity sk Chern k of e. And the rest is the same as before. So in the sense, therefore, you take the cap product, you change the virtual fundamental cycle by taking its cap product with this the general multiplicative characteristic class of the Hodge bundle. And the result depends on parameters. S1, effectively, it turns out S1, S3, S5, etc. So that on Sk with odd k. And the question is, well, now therefore this function incorporates all the previous invariants, but also intersection indices of all these classes with arbitrary products of components of Chern character of the Hodge bundle, therefore arbitrary characteristic classes of this Hodge bundle. And the question is, can you compute them, this new invariants, in terms of the old ones, where this all s is equal to 0 and this factor isn't there? So that's the question. And here is the theorem that they prove. It says that, well, if you, so there is this family of such descendant potentials, such partition functions, depending on this parameter s. And if you differentiate in this parameter s, the evens, with respect to evens, it doesn't matter, it's just zeros, but with respect to the odd parameters, that's the answer. So it can be expressed, this derivative can be expressed in terms of that family is a differential equation. This is Bernoulli number, and this is some differential operator. And here is an operator. So first of all, what's the proof of the theorem? The proof is the same as Mumford's theorem, literally the same. So we just apply Grothendieck Riemann-Roch formula. Namely, what you do, you take, okay, you want to compute push forward of the trivial bundle here no, really, not that. So it's a derivative. So differentiate in S12 minus 1. So what happens, this corresponding components of Chern character appears in front of the integral, right? Now, it is a component of Chern character, but it can be computed by there is the Riemann-Roch formula as cohomological push forward of something from the next moduli space with the next mark point. That something is the Todd class of the relative tangent bundle, but it is a computation is the same as what is it as what we discussed here. So it is kind of it's a similar computation. So the geometry is exactly the same. There is nothing essentially new there. But instead of so what Mumford did, he computed the class as some push forward, but right now we are dealing with integrals over spaces. Therefore, instead of so you have this components of Chern characters push forward from there downstairs, instead of computing it here, you can pull everything back to that space and compute integrals there. And that's how you get the right-hand side of this expression. So that so what is this operator? First, let's look at the notations. First of all, there is this red index. It is just an index in the basis in cohomology. Let's phi mu be basis in the cohomology of the target space, and Ti mu are the coordinates. So this Tk are cohomology classes, but now I'm expressing them in terms of some basis. And the summation over that index is suppressed. There was not enough space here, so I'm using kind of Einstein notation. So when there is this red indices repeating correct indices, there is summation over them. Suppressed there. Now, this node means that it's the basis element is 1. And so when you differentiate in the direction of that node, so what does it mean you differentiate this kind of correlate in the direction of T node? It means that T2L node. 2L, it means that it is a coefficient at psi to the power 2L. Psi to the TL, it's a psi to the power 12. And to not mean that coefficient is 1 in front of it. So it is exactly as in the Mumford's formula, you would get this, this term. It's psi 2L, but instead of pushing it forward downstairs, you just pull everything up and integrate against it. That's therefore this term comes from, therefore this term corresponds to this derivative. And now this term is exactly what you will get from this Mumford's correction here. It is that same expression, except that now we see that when there are two curves, so when there is a curve with self-intersection or with two curves with intersection, actually, what do you mean parameterize them by moduli parameterizing this curve and that curve? You need also that the curves in the target space go through the same point. Therefore, you need this diagonal constraint, that evaluation at this mark point of this curve and evaluation at this mark point of that curve, they in x times x, they lie on the diagonal x. So the diagonal x and x cross s. Therefore, you need to, so this diagonal constraint that they land at the same point, cohomologically expressed by this Poincare intersection pairing. So this G mu nu, it is a matrix inverse to matrix of Poincare intersection pairing in this basis. And this term that was not present in the Mumford formula is because we have now not 0 and 1 mark point, but we have n and n plus 1 mark point. And the point is that when you have some psi classes here, but you need to pull them up back upstairs, then they're not exactly the same psi classes as psi classes with the same names there. It's because the curve, where is it? The curve gets modified when mark points hit, one mark point hits another. So they're slightly different. And the corrections come from the corrections that come from this. They are expressed this way. But there is therefore this second order differential operator here, and this formula implicitly therefore computes all this kind of determines all this new invariants in terms of old ones, and then you should just stare at this formula and think what it might possibly telling you. And first of all, it's a kind of infinitesimal way of describing things. You're differentiating a parameter, and it's equivalent to applying some operator in the other variables of this function, right? But if you formally integrate this differential equations, then the answer should look like that. There is this d, the standard potential with s equal to 0, with no this Chern components, so just usual invariance, and then you apply this flow that e to the sum s12 minus 1. This is, I forgot to put this coefficient there, delta L. So there is this kind of, yeah, if you think of s as time variable, so there is this flow with many time variables, and that's how this function is expressed in terms of ds, in terms of d. Yeah, right, if you start differentiating in this, exactly this in SL12 minus 1, these operators will occur there. That's all nice, except that if this formula kind of makes sense if these operators commute. I'm not sure that Faber and Penderipane even bothered to check whether these operators commute, but they better do so, that they better compute with each other. And so this formula makes sense. But also, what kind of operators are these? They kind of look in some sense very simple. Because you see what is here. This is, so first of all, it's a second order differential operator. There's first order derivatives, multiplications, and second order derivatives. So it looks like a quantization of some quadratic Hamiltonian, right? So if derivatives, if this multiplication operators stand for coordinates and derivatives stand for momenta, then this is kind of quadratic in momenta, and this is first degree in momenta and first degree in the variables operator. Now the combinatorial structure here is kind of simple. You see that it's a sum, it's an infinite sum. I is from 0 to infinity. And the name of the derivative, the index of the derivative, is shifted comparing to the name, the index of the multiplication operator of the variable by the same 2L minus 1. It's just the same constant. Then if you look what happens here, you see that it's kind of this pattern. Here there are finitely many terms here, but in some sense this pattern persists. It's also sort of, you think how this indices are related, there is also some kind of the sum of these indices is 2L minus 2. So there is something suggestive in these formulas, and you wonder what kind of symplectic geometry and quadratic Hamiltonians and quantization is behind, and so that's what we'll discuss next. It turns out that there is, so that kind of the importance of this theorem from my point of view is that it's very suggestive of very simple formalism that we'll discuss next time. It's a symplectic loop space formalism, which is some kind of language, some notations, which into which all identities between generating functions grown within theory fit nicely. In particular, this theorem of Faber and Penderipane becomes very simple to formulate, and once you have it at hand, then that formalism at hand, then you actually can apply it to many other situations. For example, you can ask, apply the gradientic Riemann-Roch formula not only to the trivial bundle, which produces Hodge bundle, but but to anything, essentially, some other bundles and push them forward. And that's what quantum Riemann-Roch formula is eventually about. Therefore, that what we're dealing here is some very special case of quantum Riemann-Roch formula, but to make it look nice as a part of general theory, we need some formalism that we'll develop next time. Thank you.